Now let's understand the mechanism of fastening or clamping. How does torque applied on the bolt convert into a joint? So let us consider this joint having two plates, and these two plates are assembled together using a bolt and nut. So this is the bolt in the cross-sectional view and this is the nut. So the bolt is first inserted from the top and engaged with the nut, and it is rotated freely. Once we rotate it, we will reach a point at which it requires a lot more effort to actually rotate the bolt. So this is the torque which is being applied, and this torque which is being applied will start generating a compressive force onto the plates as shown over here. So the torque which is applied will generate a force at the contact of the bolt and the nut with the respective plates. So there will be compressive forces which will be generated, and these compressive forces will lead to the clamping of the joint. So the key question to ask is, what happens when you tighten the fastener by applying the torque? What exactly happens internally inside the components? The first thing is that the bolt head and the nut will impinge the compressive force onto the respective plates, whereas the bolt internally will develop a tensile load. So internally the bolt will develop a tensile load which is tending to pull it apart as shown over here. So while the bolt and nut impinges the compressive force onto the plates, the bolt internally will have a tensile load which is acting inside it. So this tensile load is induced due to the application of torque, and it is called as the preload. This tensile load is very critical for the integrity of the joint. This load increases as more and more twisting moment or torque is being applied, and it can reach as high as the elastic limit of the material. In many high strength applications, this preload or internal tensile load can reach to levels of elastic limit of the material for very high torque values, and it can also damage the bolt if the torque is applied excessively. This internal tensile load which is acting inside the bolt will be equal to the compressive load which the bolt impinges onto the plates. Bolt and nut impinge onto the plate respectively. If there is no external loosening which is happening outside the joint, the maintenance or retention of this internal tensile load inside the bolt will make sure that the clamping is taking place and the function of the fasteners is satisfied. So irrespective of the external loading, the preload will always remain and maintain the integrity of the joint. If the preload or the internal tensile load is lost, the integrity of the joint will be lost. So if we separate the plates and the bolt, we can understand the free body diagrams of each. So when the torque is applied, there will be compressive forces which are acting onto the plates as shown over here. If you are considering the two plates as a spring, then the spring will compress. And the bolt, if you are considering the bolt as a spring, the internal tensile load will tend to expand the bolt. The analogy of the plate material and the bolt material with respect to a spring is because the deformation is generally in the elastic range. So when the deformation is in the elastic range, then the material acts like a spring with a stiffness K, which is a function of the geometry. So because of these loads, the compressive loads on the plates and the tensile loads on the bolt, there will be displacement. The displacement which the plates undergo will be in compression. The displacements which the bolt will undergo will be in tensile. So if you are plotting the graph between load and displacement, here load is in y-axis, displacement is in x-axis. So if you plot the graph for the bolt from this point where the load is 0, then the load is gradually increased as we keep torquing the bolt, and it reaches a maximum point which is indicated over here. And for the plates, At zero load, there will be zero displacement. And as the load is increased, the displacement will also increase and reach a point over here. So as you can see, the level of the load in the y-axis for both the plates as well as the bolt is the same, which means that eventually these two forces cancel each other out for static equilibrium. Important point to note over here is the two graphs will not have the same slope. They will not have the same stiffness because of the difference in the geometries for the plates as well as the bolt. To maintain the integrity of the fastener joint so that it does not separate, it is very important to understand the joint stiffness. So the joint stiffness is basically the combination of the fastener stiffness and the stiffness of the two parts which are being clamped. So here is an assembly which shows two plates of variable thickness. One is the cyan color plate and one is the green color plate. Both are being clamped using a bolt, a nut and a washer. Washer is this one, which is shown, which is used to expand the area of clamping. The washer has a thickness of T. The length of the members which are in the clamping zone, which undergo compression, is called as the grip, which is shown over here by small l. So this small l has the component 1, which is a cyan color, component 2, which is green color, and also the washer, which is these three are sandwiched in between the nut and the head of the bolt. The bolt has a non-threaded portion and a threaded portion. The non-threaded portion, which has a major diameter as shown, which is a shank diameter, it is called as the shank. Non-threaded portion is called as the shank. Length of the non-threaded portion is LD and length of the threaded portion is capital LT. Here, this is the length of the threaded portion, capital LT, and small ld is the length of the non-threaded portion. Small lt is the portion of large lt or portion of the threaded portion of the bolt which comes within the grip. So the grip is, as we have seen, it is small l. From this point to this point, the sandwich components are called as grip, and that length, if the threaded portion comes in that length, then that threaded portion which is coming into that grip is lt, small lt. H, capital H is the height of the nut, T is the thickness of the washer, and capital L is the total length of the fastener or the bolt. So capital L includes the non-threaded portion, which is the shank, as well as the threaded portion. So capital L is equal to small ld plus capital LT. Next, let's have a look at the areas, the cross-sectional areas. So there are two major cross-sectional areas which are under consideration. One is the cross-sectional area of the shank. So the shank, which is the unthreaded portion, will have a cross-sectional area which is equal to pi r squared. Well, r is the major radius, or it is pi d major the whole square divided by 4, because r is equal to d by 2. So that is AD. And AT is the cross-sectional area of the threaded portion. The cross-sectional area of the threaded portion is not so easy to calculate using a straightforward formula. Generally, the data is available in standard thread data books. So from that, we can take the data for the cross-sectional area of the threaded portion for different types of metric threads. So AD and AT are very important. Now, if you are having a rod, a circular rod as shown, which is undergoing axial tension. So if it is being expanded axially, then the deflection which it undergoes will be equal to PL divided by AE. P is the load which is acting on it, L is the length of the rod, A is the cross-sectional area, and E is the Young's modulus of the material. And from this, we can find P by delta, which is nothing but stiffness. So P by delta, that is force divided by deflection, will give us the stiffness of this rod in axial direction, and that stiffness K, which is generally denoted as K, is equal to AE by L. It is a function of the cross-sectional area, the Young's modulus of the material, divided by the length of the rod. So from this, we can find out the stiffness of the unthreaded portion of the bolt, which is denoted as KD, and also the stiffness of the threaded portion of the bolt, which is denoted as KT. So KD is ADE divided by LD and KT is ATE divided by LT. Here small lt is used instead of capital LT because we are only concerned about the length of the threaded portion within the grip. So LT is the length of the threaded portion within the grip, which is under compression or elongation because of the forces from the torque. The total bolt axial stiffness is due to two portions, the unthreaded portion and the threaded portion. These unthreaded portion and the threaded portion both act like springs which are connected in series. So when we are connecting two springs in series and both the springs are having their own stiffness values K, then the formula to find out the effective stiffness is 1 by K is equal to 1 by K1 plus 1 by K2, where K1 and K2 are the stiffnesses of individual springs 1 and 2. Here the springs are indicated as the portions for the unthreaded portion and for the threaded portion. So if you are simplifying this equation, we will get K is equal to K1 K2 divided by K1 plus K2. Now instead of K1 K2, if you are replacing with KB and KT, so the effective stiffness of the bolt is KB. And in place of K1 and K2, we are replacing them with KD and KT, which is for the non-threaded portion and threaded portion. So KD, KT divided by KD plus KT is the effective bolt stiffness. And KD and KT are already known as we had earlier seen. ATE divided by LT is KT, ADE divided by LD is KD. So substituting these values and simplifying, we will get KB as a function of the cross-sectional areas of the threaded portion, non-threaded portion, the Young's modulus of the material of the bolt, and the length of the threaded portion and the length of non-threaded portion. So KB is the effective stiffness of the bolt in the clamped zone. This illustration shows us the floating fasteners. So there are two types of fasteners as we had seen earlier, floating fasteners and fixed fasteners. So this calculation stands good for floating fasteners, whereas the approach for fixed fasteners is slightly different, as we will see in the next slide.